Hi, welcome to Lecture 2.1 on chemistry and the molecules of life. So, in biology, we can study life at many different levels. So, if you recall the different levels of biological organization, we start at the smallest level, which is the molecule. The cell, however, is the smallest unit of life. And one of the things that's quite interesting is that all cells are made up out of the basic materials that are about the same. Doesn't matter if you're looking at a moss cell or a cell from a human or a fly, you'll find that there's some basic chemicals in all of them: nucleic acids, lipids, carbohydrates, proteins, and water. And to get a feel for what's going on inside a living organism, one really needs to know a little bit about chemistry. So if you actually took a chemistry class, you'll go into a lot more detail than I will be going into. I'm going to get just the basics, just enough so that you can understand a little bit about the chemistry of life. So first of all, there are 92 naturally occurring elements on Earth, and an element is a substance that can't be broken down into another substance using chemical means. And of those 92 naturally occurring elements, 4 of them are really important for living organisms: carbon, nitrogen, oxygen, and hydrogen. A nice way of remembering them is CHON, C-H-O-N, carbon, hydrogen, oxygen, nitrogen. There are other things like trace elements: zinc, magnesium, calcium, and those are typically found in much smaller amounts in the body. So let's back up and go into the most detail that you'll need. So matter is made up out of atoms, and each element is made up out of the same type of atom. And an atom has got some basic characteristics. It has 3 types of subatomic particles: electrons, protons, and neutrons. The electrons are found in a cloud and are negatively charged, and they're very tiny to the point where they almost have negligible mass. Protons and neutrons are found together in the center of an atom, a place called the nucleus. Neutrons have got no charge, and protons have got a positive charge. Protons and neutrons weigh about the same amount, and we'll call it 1. So if you had 3 protons and 3 neutrons, your total mass would be 6, for example. Now, each type of element is actually determined by the number of protons. Carbon's got 6 protons, hydrogen's got 1, oxygen has 8, nitrogen has 7. So you could theoretically make gold if you knew how many protons to jam together into an atom. So what if you took an atom and you started changing the numbers of the subatomic particles? What would happen then? Well, as I've alluded to, if you change the number of protons, it's going to change which element you have. So if you add a proton to carbon, you're going to generate nitrogen. If you change the number of neutrons, you're not going to change what type of element you've got, but you're going to change what we call the isotope. So some isotopes are radioactive, and radioactive isotopes are versions of that element that are unstable. They have too many neutrons, and those neutrons get dropped over time at a regular rate called the rate of decay. Normal carbon, for example, has got 6 neutrons and 6 protons, but a radioactive isotope of carbon has got 8 neutrons and 6 protons. So that's carbon-14. Carbon-14 is going to be important for us later in the semester when we start talking about carbon dating, which is a form of radioactive dating of organisms that are less than 40,000 years old. Electrons, these are super important because the number of electrons you have, to some extent, determines how reactive an atom is. So normally, the number of protons and the number of electrons are the same. So that means that the positive charges and the negative charges are equal to each other and they cancel each other out, so there's no charge. But If you add or subtract an electron to an atom, you can create an ion. If you take away an electron, you end up with more protons than electrons, which means that you'd have a positive charge. We'd call that type of ion a cation. If you add an electron to an atom, you're going to be adding a negative charge, and therefore the ion that's created is called an anion, a negatively charged ion. So there's something quite important called the octet rule, and the octet rule says fill the valence shell to be stable. The reactivity of an atom depends on what's going on inside a shell called the valence shell. So let me back up a little bit. When you're placing electrons in an atom, where do they go? They go into things called electron shells. These are pathways that are taken by the electrons. And each pathway has got a certain number of spaces for electrons. The inner shell, called the K shell, has got a maximum space for 2 electrons. So if you have only 1 electron, it'll go into that inner shell and you'll have space for 1 more. But what if you have 3 electrons? You would fill both of the spaces in the K shell, and then you would have to put your spare electron into the L shell, the second one. The L shell has got a maximum space of 8 electrons. The M shell has got another space of 8 electrons. Octet comes from oct, which means 8. That's where we get the octet rule. The octet rule says in the outer shell, which is normally in most of the atoms that we deal with, has got 8. If it's either got 8 or 0, your atom is no longer reactive. So the number of electrons in the valence shell, which is the outermost shell, determines how reactive your atom is. So if you have got 10 or fewer electrons, your outer shell or your valence shell will be the L shell. Whereas if you've got 12 or 13 or more electrons, you'll probably have 3 shells, in which case the M shell is the valence shell. When you have a completely full valence shell, your atom doesn't react. If you've only got 1, or if you're only missing 1 electron in your valence shell, the atom is highly reactive. And if you're about halfway full, the atom is moderately reactive. So this in part determines why some elements are really violently reactive and others are not. There's a model for atoms called the Bohr model of valence shells, and it's a way for you to sort of draw a picture of what the atom looks like so you can figure out how reactive it is. The first picture in here is group 1, and that is hydrogen. And notice that hydrogen only has 1 electron, and its outer shell is the K shell. That's the inner shell, the first one. And it could either throw away an electron and get back down to nothing, or it could grab an electron and be full. So hydrogen is a really reactive chemical. The next down is lithium. Lithium, like hydrogen, has only got 1 electron in its outer shell. So either by ejecting the electron or by grabbing 7 more, it could stabilize. The periodic table of the elements organizes elements based on these patterns. So group 14 in the periodic table has got 4 electrons in the valence shell. Group 17 has got 2, 4, 6, 7 electrons in the outer shell. Group 18 has got either 2 or 8 in the outer shell. Group 18 is a group of elements which we call the noble gases. They're noble because they don't mix, they don't react. And they don't react because they have fulfilled that octet rule. They have a full outer shell. So elements can actually combine to form compounds or molecules. A molecule is when you have 2 or more atoms bonded together. They can be from the same element, or If they're from two or more elements, we'd call that a compound. And the bond between those atoms, the way in which they glue themselves together, depends on the electrons in the outer shell. And there are three types of bonds that you can get. You can get ionic bonds, covalent bonds, and hydrogen bonds. We're going to go into those in a little bit more detail. A covalent bond forms when you share your electrons. So carbon normally has got 4 electrons in its valence shell. Hydrogen normally has 1. So if carbon shares an electron with 4 different hydrogens, it creates a situation in which the outer shell looks like it's got 8 electrons, and that decreases the reactivity of the carbon, and you have a stable molecule. That molecule is methane, CH4, 1 carbon, 4 hydrogens. The number of covalent bonds that atoms can form depends on those valence electrons. Carbon can form 4 covalent bonds, oxygen can form 2, nitrogen can form 3, and hydrogen can form 1. This is something that's going to be important for you in your lecture activity called carbon bond. Now, one could draw out every molecule showing the positions of all of the electrons, but that would take a lot of time. And so to make things a little easier and to draw things faster, typically biologists and chemists will represent a covalent bond by a single line. So if you look at the methane molecule that's drawn in formation at the bottom right of your screen, you will see that it says CH4, and each line represents a single covalent bond. A single covalent bond is 2 shared electrons. Ionic bonds are a little different. In this case, the atom completely sheds an electron or completely gains an electron to form an ion. Anions are negatively charged and cations are positively charged. And when you have weak positive and negative charges, they attract to each other, and that attraction forms a bond. Compounds that are made with ionic bonds typically form crystalline structures. So table salt and sugar have got bonds within them that form in this way. Hydrogen bonds are your weakest form of bond, but by no means are they the least important. Hydrogen bonds are going to be really important for a variety of different things later this semester. So I want you to think about oxygen, and it's got its electrons in its outer shell. But oxygen is bigger than hydrogen. It has a bigger nucleus with more neutrons and protons. And as a result, its ability to pull electrons towards itself is stronger than hydrogen. So we would call oxygen an electronegative atom because it pulls those electrons towards itself and it makes itself slightly negative. So the symbol above the oxygen is delta negative, and that means a partial negative charge. So what happens is if you were looking at a single water molecule, which is made from 2 hydrogens and 1 oxygen, is that the oxygen side of the molecule will be negatively charged and the hydrogen part will be positively charged. So this results in weak electrical attractions between neighboring water molecules. So water can have some structure to it, and this has some significant effects for the biology of life.